Okay, so thank you for coming. I am Kensuke Harada from Osaka University, and today I would like to talk about the robotic manipulation aiming for industrial applications. Okay, let's start. This is one of the very typical first slide of the robotic presentations, saying that the industrial robot work in the structured environment and perform the repetitive task. And it may give the impression that the research on industrial robot is easy and simple, but I think that it is not always true. And Japan front the problem of lack of laborers. And as you can see from this figure, in this figure, the x-axis is the year, and the y-axis is the population. And the dotted line shows the current situations. And the blue area it means express the working population. And from these 50 years, the working population will be decreased from 77 million to 45 million. So this is a very big social problem in Japan. So I think that robotic manipulation is the core of solving the problem of lack of laborers. For example, in the robotic product assembly, human workers try to assemble the product by manipulating the part. And in service retailer, such as convenience stores and supermarket, workers try to put the item on the shelf and rearrange the item in the shelf. And in the logistic warehouse, a human try to extract a target item from the shelf and put it in the box and send it to the customers. And in food industry, this is the arrangement of the bento box. Human workers try working hard to put many foods in the bento box. And this is a very, very hard task. But I think that everything is related to robotic manipulation. And this is an example of the research works done in our laboratory. For example, we research the assembly task. And this is an example of the assembly task planning. And this is the force control assembly. And this is an example of the picking task. And this is an example of the lab automation. And this is hand grippers and sensors. And as an application, we also research the human assistance. And among a lot of topics, today I will focus on just two topics. One is the industrial bin picking, and the other is storing knowledge on robotic system integrations. And first, I would like to talk about the industrial picking. So we mainly talk three topics: picking or separate tangled parts, and picking wire harnesses, and collapse prediction. And in case of industrial bin picking, it poses a bit different research topics compared to the picking task of the daily items. One of the typical examples is here. The industrial parts usually have a very complex shape, and it means that even if the robot tries to pick one of the parts, it gets entangled, and the robot may likely to pick more than two parts. So we are focusing on this kind of problems, and this is the typical grasping strategies. And I think that it would be better if we can find the isolated parts and then try to pick the isolated parts one by one. But after picking the isolated parts one by one, there is no parts. There is no isolated parts remaining. So in that case, we have to actively disentangle the tangled object. So this is the strategies. So we consider this is the main bin where the part is stored, and this is the goal bin. And we, in addition to 2 bins, we consider the buffer bin. And first, we try to predict if the entanglement occurs by using the neural network, so-called PICnet. And then if it finds that the entanglement doesn't occur, then the part is moved to the goal bin. And if not, we temporarily put it into the temporary bin, and then pick once again. In this case, if the entanglement is solved, we pick it to the move it to the goal bin. And if not, we use the neural network solved PULNet to actively disentangle the tangled object. So this is the experimental result. First, we predict the isolated object. And then, if the isolated object is found, we directly grasp the designated part. But in this case, there is no isolated part, and once put it into the temporary bin. But in this case, the entanglement was solved, automatically solved. And then like this, like this. And finally, in this case, even if a robot put the object to the temporary bin, the entanglement wasn't solved. In this case, we use the neural network, so the PULNet, to actively disentangle the entangled object. Okay, so then we consider a more complex case. So this is a collaboration with the automobile company. So in the automobile company, there are many industrial parts to be supplied to the assembly line. So this is an example of the wire harness. So wire harness is usually supplied by like this state. So this state is the wire harness is very, very heavily cluttered, heavily entangled. And as shown in the video, we asked some students to try to extract one wire harness from the bin. So some students tried to shake the wire harness to solve the entanglement, and another student tried to use dual arm to solve the entanglement. And one of the students tried to use the circular motion to solve the entanglement. Then we focus on the circular motion performed by robot to solve the entanglement. So we consider 2 kinds of motion primitives. One is so-called helix motion, and the other is called the spinning motion. So in case of the helix motion, we consider how many circles should the robot draw. And also in the spinning motion, how many times the robot spins the object. So this is the overview of the method. First, we take the depth image. And then we detect the candidate of the grasping pose by using the neural network so-called ASP.NET. And then we select the action to be likely to disentangle the entangled wire harness. So this is the experimental result. By using the circular motion, it can be seen that the robot can effectively disentangle the entangled wire harness. Okay, so the success rate of this method is not very low, is not low, and about 84%. I believe that it is high enough for picking such a very difficult object. And in this method, there is no feedback after the robot pick up the object. Then we use the force feedback in the picking task. First, detect the grasping pose. And then in this case, we use the wrist force sensor. And according to the information of the wrist force sensor, it is detected that the entanglement occurred. The robot stopped. It stopped. And then the robot tried to shake the object. And if there is almost no change, the robot used dual arm to pull up the object. And then the robot tried to move the object to the goal pin by monitoring the force sensor information. And we iterated this step until the robot successfully carried the wire harness to the goal pin. And this is the experimental result. In the left-hand side, we show the experimental result of the relatively shorter wire harness. And in the right-hand side, we show the experimental result of the relatively longer wire harness. In both cases, the success rate is not very bad, more than 90%. Okay, so in the shorter wire harness, the success rate is almost 97%. But in the longer case, it was a bit difficult, and the success rate is almost 80%. Okay, so let's move on to the next talk. We consider the case where a lot of items are randomly stored in a shelf. And in this case, if we try to extract one item from the shelf, the other shelf, the pile collapses, and the other items get out from the shelf. We want to avoid such a situation. And this slide shows the overview of our method. And we usually use dual arm to safely extract one item from the shelf. So in this figure, we use the right arm to support the neighboring items, and then by using the left arm to safely extract the target item from the shelf. And we use the neural network so-called the collapse prediction network. And by using the physics simulator, we train the neural network to predict if the pile is going to collapse. So as shown in this figure, in the top we show the depth map, and in the middle we show the object to be extracted, and in the bottom we show the object to support. So by combination of these depth map and the object to extract and the object to support, we predict the pile will collapse or not. And this is the experimental result. And in the left-hand side, First, we support one of the objects by using the right arm, and then extract the target object by using the left arm. I'm sorry, but in case of this experiment, we asked students to perform to move the robot as slow as possible. So the motion is quite slow, but I think that we can make it faster. And in the right-hand side, by applying this method for the rearrangement of the shelf, so by rearranging the shelf and then put another item to the space. Okay, so let us move on to the second topic, storing the knowledge on the robot system integration. So we want the robot to distribute in many areas and many small companies. So this slide shows a typical case where in the left-hand side, the human workers perform the task. So we perform this task by a robot. And in the right-hand side, we show the case where the robot performed the task. So to construct such a robot system, we need the so-called system integration. So system integration typically composed of the specifications and the design and the manufacturing and test. And the total cost of the system integration is composed of the cost of the robot and the cost of the equipment and the cost of the system integration and maintenance. The problem is that the cost of system integration is very high, and it should be reduced. So this is how to solve this problem. So we had better, we are currently constructing the database of knowledge. So the database is composed of the object type, and the robot type, and the robot hand, and the handling motion, and many knowledge related to the robot, related to constructing the robot system. So in this case, a user asks the database to construct a robot system to automate the task. And then the database answers the solution, which robot to use, or which hand to use, or which motion to use. And the user can freely update the database by adding the new experience or new product and new robot and new hand. So we try to commonly use database in any industry and services. So this is a part of the Roboship project. Actually, Roboship is the union of Japanese 9 robot companies, including Kawasaki, Denso, Fanuc, Nachi, Fujikoshi, Mitsubishi, and Yasukawa, Epson, and Daihan, and Panasonic. And this is the national project, and there are many main projects. One is on the handling and the motion planning, and the second topic is remote control, and the third topic is new material and sensor applications. And our Osaka University belongs to the project 1 and working on the handling and motion planning. And mainly, we work on how to use the stored database. And throughout this research, we propose the method so-called the similarity matching. So this slide shows an example of the service retailer. So service retailer has to deal with 1,000 of items every day. But for the robot to deal with such thousands of items, we need the database of database of items. But it is not realistic to prepare 1,000 and 10,000 or 100,000 model of the items. So our approach uses try to find the similar object. And by using the model of the similar object, we try the robot to perform the task in the service retailer. So this slide shows the overview of the method. Our method is so-called ontology-based similarity matching. In the top part, is the ontological part, and we first find the similar object by using the ontological information, and then we find the candidate of object similar to the target object. And then in the bottom part is a geometric class, and among the candidates, we select some object where the size shape is resemble to the target one. So this is the experimental result. So this is an example of grasping a PET bottle by using the model of the baby milk. And this is an example of grasping a dish by using the different dish. This is an example of grasping a computer mouse by using the model of the dolphin, and so on. So by using a different model, the grasping task can be performed. So this is also the example that the can of the tennis ball can be grasped by using the model of the drinking can. And the PET bottle can be grasped by using the 3D model of the shampoo. So this is the example of grasping the snack by using the different shaped snack, but similar. Okay, so let me wrap up the talk. And we want to realize the full automation. And we will consider what is needed for the full automation of the task. We believe that task and motion planning should be placed in the center. The task and motion planning composed of the task planning and motion planning, and also grasp planning is also considered. And in the task planning, task is planned, and the motion planning, trajectory is planned, and in the grasp planner, the grasping pose. But it is not enough. For example, we have to construct the gripper or hand adequate to perform the task. And in addition, we need to apply the human skill to perform the required task. And it usually includes a force application, and the force control is needed to realize such task. But this is not enough. So all the information of the environment is not usually available. So I think that machine learning is very essential to solve the uncertainty problem. And to use the machine learning, we need the database. So this is the milestone to realize the full automation of the task, which is in mind. Okay, so thank you very much. This work is done by in our laboratory. This is the faculty members and students and collaborators. Thank you very much.